Hello and greetings. My name is Pilemon Vinci Anamini, and my group members are Muhammad Muzaini, Muhammad Zulfikar, Muhammad Iman, and Hafiza. In today's video, we'll be presenting about our findings on our alternative assessment. In this video, we will be present about the introduction of our assessment, our problem statement with our objective, our methodology, which is the two methods that we use to find the result in this assessment, our findings, and finally our conclusion. So what is electroencephalogram, EEG? An EEG is a scientific study which to monitor brain activity. Usually the result of this brain activity will be appear on a screen as a waveform. These methods are used to diagnose brain tumor, brain damage, brain dysfunction, brain inflammation, stroke, and sleep disorder. Our problem statement of this assessment are the EEG signal that are taken from the individual sometimes have some information that are lost or missing. Because special information is lost, the signal picked up from the scalp are not always an accurate depiction of the impulse coming from the brain. Next, EEG data has a lot of noise in it, which might mask weaker EEG signals, and data can be contaminated and distorted by artifacts such as blinking or muscle movement. Lastly, is during EEG recordings, it is necessary to distinguish between significant brain signals and random brain activity. Our objectives are first to understand what the EEG signal is. Next is to learn how to read EEG signal and how to pre-process it by using MATLAB. And finally, to compare and decide which filter is best to pre-process the EEG signal given.
Assalamualaikum, I am Muhammad Zulfikar bin Sulaiman. I'm going to demonstrate on how we import and extract the data and filter it using method 1. First of all, we import the data from the raw file folder to the EEG lab. So for this example, we are going to use the S04 raw data. Click OK for the pop-up windows. So we are going to name this file as S04. Click OK. Then we are going to enable the channel location by clicking at Edit and Channel Locations. We are going to use the MNI coordinate file for BMD fit model because BSA file for Fusion deep fit spherical model is obsolete nowadays, and MNI coordinated is better for this one. Click OK, and this for this pop-up windows, just click OK. Next, we plot the channel location by name and by number. So now we compare and find the channel for P7 and P8. So now we know P7 is 11, P8 is 20. So we go to edit and select data because we just want our desired data and put 11, 20 at the channel range. Click OK. We're going to name it as S04 raw. See, the channel per frame is now changed to 2. Next, we are going to filter the data. First, we plot the channel data scroll. Click display, remove DC offset and normalize it to standardize. And now we get the raw data for P7 and P8. Put that aside. Next, we click tools, filter data, basic FIR filter, and use the range of delta, theta, alpha, beta, and gamma. For the sake of simplicity, we are going to make only delta filter, which is the range of 1 Hz to 4 Hz. Click OK, and this should okay. Now I'm going to change this to S04 delta. Okay, now plot the channel data scroll and normalize it. Okay, so this is what we get. The right side is the original or the unfiltered data or signal, and the left side is the filtered data. So for every range, which is theta, alpha, beta, and gamma, the same way is applied. Next, we are going to take this figure and put it in a table like this. So we already filter the S04 signal. So this is how the original look like: delta, theta, alpha, beta, and gamma. So for other signal that are given to be filtered, the same step are applied and just repeat it.
I am Hafiza and I will explain the method 2 for this assessment. For method 2, we follow the similar step of importing the dataset until extracting the data, just like in the method 1. However, for the filtering part, we filter P7 and P8 using a band pass filter of the range of 1 Hz to 40 Hz, since delta until gamma waveform present in that frequency band range. Next, plot the channel time frequency for each P7 and P8. Then, in this window, select Use the actual frequency function and click on the plot curve at the frequency. This function will plot time frequency curve at the given frequency's baseline. The frequency limit baseline of 3 Hz, 6 Hz, 10 Hz, 22 Hz, and 38 Hz were chosen according to the median of EEG subband frequency of delta, theta until gamma. And then click OK. The new window surface on the screen will show the comparison of every frequency baseline. In other words, it shows which frequency subband holds the majority in the signal. This information was further analyzed and tabulated. The way we tabulated it was by comparing and finding the highest frequency baseline for each P7 and P8. For example, as we can see here, the highest value of frequency baseline is in 3 Hz with a value of 32.0349 decibels. Therefore, based on all type of frequency band range, 3 Hz is located in the range of delta. Hence, in the table, fill the orange color, which indicates the highest baseline on the delta box for P7 for dataset signal 4. Last but not least, repeat the same way for analyzing the data P8, and we can get the result of high value of baseline at delta 2. Color half part of the box with the red color to indicate the high intensity that located at delta frequency range for P8.
Hello, Assalamualaikum. My name is Muhammad Muzaini and I'm going to present on the findings that we get. To be precise is Method 1 finding, the signal analysis. From the pre-processing method 1, we managed to decompose the EEG signals into separated subband frequency. Hence, we could also identify the patterns and characteristics of the EEG subband. As in the table, we managed to summarize our finding. First is the delta. Delta activity is predominantly found in infants, or we can say in baby. Delta waves are associated with deep stages of sleep in older subject, and that's why we managed to get a lighter and smoother signal. Moving on, theta signal frequency of 4.8 Hz is associated with mental inefficiency and represents a daydreaming. When a person performing a routine task, the mind can disengage because the person is automatically perform the daily call. Theta has higher amplitude than alpha because theta doesn't engage with mind. If theta waves occurs at other times, they may indicate cerebral dysfunction. Next, alpha signal frequency of 7 until 13 Hz, often associated with state of relaxing when closing the eyes and disappearing when opening the eyes or alerting by any mechanism such as thinking or calculating. The wave simply indicate that you are in a state of wakeful rest. Alpha waves fit in the middle of the spectrum between theta and beta waves. Theta is dreaming, beta is fully awake. It is in the middle. Furthermore, beta signal frequency of 13 until 30 Hz is found to be less intense than gamma, as it is associated with being conscious or in an awake, attentive, and alert state. Low amplitude beta waves associate with active concentration or with a busy or anxious state of mind. Last but not least is gamma signal frequency of 36 until 40 Hz. It is associated with high intensity brain tasks such as visual processing, problem solving, and memory, and thus the signal was found to be much compact and denser compared to the other frequency band.
Assalamualaikum. My name is Muhammad Iman Saufi bin Nordin, and I will present about the filtered signal classification, which include in the findings, and I will also present for the conclusion. The table above depicts the frequency ranges of emotion states during the normal, abnormal, and deep sleep stages. It is clear that the frequency ranges of the emotion state correspond to the frequency ranges of brain activities. For normal frequency ranges, it is the same with alpha, beta, and gamma frequency ranges. For abnormal, it is the same with theta frequency ranges, and for deep sleep stages, it is the same with delta frequency stages. The emotion state of the signals can be classified, yielding the results shown in the table above. As we can see, for signal 15, it is in normal frequency range state. For signal 2 and 3, it is in abnormal frequency range state, and for the other signal, it is in the deep sleep frequency range state. However, a normal EEG brainwave signal does not rule out the possibility of internal brain abnormalities. Normal or abnormal. According to Epilepsy Foundation, someone who has seizures on a weekly basis can have a normal EEG test. This is due to the fact that the EEG only records brain activity while the test is being performed. If the person is not having a seizure at the time, the test may not detect any abnormal brain waves. The electrical activity is abnormal during a seizure. In most people, once the seizure is over, the brain quickly returns to normal. When an EEG is performed several hours or even days later, the changes in electrical activity that occurred during the seizure are missed. The same is true for the brain's abnormal and deep sleep states. Conclusion. To summarize, two methods were used to filter the EEG signals. The first method is appropriate for part 1 of the assessment, which is to remove noises from the EEG signals. It has been demonstrated that the first method produces a clearer signal waveform. The second method is appropriate for part 2 of the assessment because it can detect states of brain activity. As a result, the state of the brain waveform can be classified as normal, abnormal, or deep sleep. Thank you.